Thank you for the introduction. Today I will talk about background calibrated MEMS gyroscope. So here is the outline of my talk. First, I will talk about the problems of MEMS gyroscopes. Then I will talk about the solutions in the literature. I will give to talk about our method, background calibration. Then I will give our test results and conclude my talk. So let's start with the problems of MEMS gyroscope. So the MEMS gyroscope is basically trying to measure the angular rates. That is basically omega here. And at the end of the day, we want to get the digital output from our gyroscope. So we have input and output. So in this input-output relationship, we have slope that is called scale factor, and we have also offset. It is called bias. So the problem is that both scale factor and the bias depends on several parameters. And some of these parameters are coming from the transducer and the other parameters are coming from the electronics. And the problem is that all these parameters depend on environmental conditions, such as temperature, stress, voltage supply, acoustic, vibration, linear acceleration. So it is a big problem for MEMS gyroscope, because for high performance gyroscope, we really want high resolution, and all these parameters degrade the accuracy of the gyroscope. So when you look at the market and the literature, you can find commercial gyroscopes. They are really small, they are really low cost, relatively low power, but the problem is that the performance is not great. And if you want to improve the performance of these small gyroscopes, basically what you need to do is first you need to increase the size, or you need to increase the cost of these devices by using expensive fabrication or some advanced trimming techniques, or you need to increase the power in the electronics. But what we would like to achieve is to improve the performance, but without doing these things. So in our work, we use background calibration. So the gyroscope, as you might know, is basically a 2-degree of freedom oscillator. So if you have two oscillators, and in the conventional gyroscope, one of these oscillators is called drive mode, and it is just an oscillator and with amplitude controller, so it's a self-sustaining loop. And in the other channel, we read the information. And we can read the information from the displacement output. This kind of gyroscope is called open loop gyroscope. Or we can get the information from the force input, and it is called the force feedback gyroscope. In the conventional approach, the problem is that we only measure one port among these 4 ports. So, and we don't do anything for the other ports. In the background calibration technique, what we do first, we apply some the calibration signal, and then we make some observation. And the relation between this observation and the calibration signal tells something about the errors in the gyroscope. And we are doing this thing in the background continuously without interrupting the operation. So this is really a low-cost solution to improve the gyroscope. Now I will talk about the details. As I told before, scale factor is one of the important parameters for MEMS gyroscope. But the scale factor is a fundamental problem. But before understanding what the problem is, I think we need to answer the correct question. And this question is this: what does gyroscope measure? So if we would like to measure, for example, Earth rotation, what will be the output of the gyroscope? In the ideal case, it is 1 rotation per 1 day, right? And what is this? It is in fact the frequency of rotation. And we know that rotation is a dimensionless quantity. So in fact, gyroscope measures frequency. So it is nothing else, it's just frequency. But what do we measure in reality, in practice? We are measuring some voltage. So of course we use some ADC, but at the end of the day we are using some voltage, and after the ADC we are getting some digital number. But the problem is, as I said, the gyroscope by itself needs to measure frequency, and there's a discrepancy between what we want to measure and what we measure. So it is a big problem for scale factor. So what is our motivation to get the accurate scale factor? So we need to know the unknown relation between this frequency and some digital code or voltage. So what is our method? So what we are doing is we are applying some digital number to as a calibration signal. Then we are trying to change the oscillation frequency, and we want to do in the drive mode because the sense mode carries the information, so we don't want to interfere with the sense channel. So in the previous presentation, the presenters also talk about these tunings. It is a very common technique in MEMS resonators, right? It is easy to change the oscillation frequency. What we are doing in our work is a little bit different, but the concept is same. So we know that it is easy to change the oscillation frequency by applying some voltage. So our concept is basically is this. So the thing is that, okay, now we get the logic, I think, because for the scale factor of the gyroscope, the relation between the frequency and the digital code is not known. But now what we are doing, we are applying some digital code and change the oscillation frequency. Okay, the logic seems fine, but what about the result? So when you look at the closed loop, the scale factor for force feedback gyroscope, you will see this expression. So it's a well-known expression. And it is depending on the velocity amplitude, it is depending on some voltage reference, it is depending on the electromechanical conversion gain. So all these parameters, as I said before, depend on environmental conditions. What about the scale factor estimation in our method? It is this. When you make the math, if you look at the paper, you will see the derivation. So it is really interesting. It is almost same as the real scale factor, so it's really good estimation. The only difference is that in the real scale factor estimation, factor expression, we have this K factor. This K factor is angular gain. That is, it is a really robust parameter. It just depends on the geometry of the structure. When you design your sensor, in fact, you know what that value is. The other difference is this eta y and eta x. So these are different because we measure our information angular rate from the sense channel, but we are making calibration in the drive channel, as I said. The good thing is that they are in the same sensor, so they will track each other really good, and they will cancel the common mode errors, like the common mode packaging stress, common mode temperature effects. So if it is capacitive sensor, it will cancel the proof mass voltage. If it is a magnetic sensor, the magnetic field will be same for both these parameters. So it is really a good way to estimate the scale factor, and I will share the test results soon. So now let's talk about the bias errors. So if you are familiar with gyroscope, there are basically two big error sources. The first one is called anisotropic stiffness, that is also known as quadrature error. Unfortunately, quadrature error is really big. Sometimes it even exceeds the full scale range. But the good thing is that there is 90-degree phase difference between the quadrature error and the rate component, that is also known as Coriolis force. But the thing is that, okay, you can maybe suppress the quadrature error by using phase-sensitive demodulation. But the problem is that even if you have very small amount of phase error, you will have a big amount of offset at your output. So quadrature is a big problem for gyroscopes. What about anisotropic damping? So anisotropic damping is smaller comparing with quadrature error, but the thing is that it is in phase with your rate component. So it's a very fundamental error source for MEMS gyroscopes, conventional MEMS gyroscopes. So in order to improve the performance, we really need to suppress these error sources. So let's talk about quadrature error first. So we are using force feedback gyroscope because it has better linearity and better range. So in the force feedback gyroscope, we are trying to rebalance the forces in the sense channel to ensure that there is no motion in the sense channel. And we know that there are two forces. The first one is the Coriolis, the other one is the quadrature force. And we are applying electrostatic forces to compensate them. Unfortunately, if you have some phase error in the system, then you cannot compensate these forces. So, in other words, the force that you apply wouldn't be aligned with the real forces. In that case, the quadrature error will lead to your information channel, the rate channel. And if we want to give some example, assume that the quadrature is 100 degrees per second and you have a phase error of 1 degree, it will cause an error of 6,000 degrees per hour. It's an offset. Assume that 1% of this offset drifts. It means that it's 60 degrees per hour, and it's really big if you want to get, for example, 1 degree per hour gyroscope. So quadrature is a big error source. So what is the solution? The most common solution in the literature is the quadrature cancellation by using some dedicated electrodes. Unfortunately, these electrodes are not available in most of the sensors. So here what we are proposing is phase error correction. So the idea is this. So we are in, again, drive mode. This drive mode, as I said before, is basically a self-sustaining loop, and you have an amplitude controller, and you regulate your velocity or amplitude by this red force. This force is the force which is in phase with the velocity, so you are regulating the velocity amplitude by means of this force. But in scale factor calibration method, so we thought that we are also applying some extra calibration signal. So, and this signal will generate some force. In order to change the oscillation frequency, that force is needed to be in phase with the displacement. So this is why it is orthogonal to the red force. So it is good, okay. So assume that, for simplicity, assume that the force is, the damping is 0. And now assume that we have some phase error, as in the previous case. So our forces is rotated here. And as I said, if the damping is 0, the total force will also be 0. And if it is the case, you can easily estimate this phase error in your system. It is just set by the ratio between these forces. And the good thing is that these forces are observable because you apply these forces. So even the damping is not 0, you have a little bit complicated expression, but still all the terms here are also observable, like the frequency. You can observe the frequency. So now, since we know our phase error, we can now compensate the quadrature leakage. Okay, now we eliminate the quadrature problem, but we still have this anisotropic damping. As I said, in MEMS gyroscope, it is a fundamental error source because it is inherently in phase with the rate component. So the interesting thing is that anisotropic damping, the reason for anisotropic damping is damping. And there should be some correlation with isotropic damping. So, but is there a way to observe isotropic damping? Yes, it is, we know, because in the drive loop, the amount of the force to sustain the oscillation is a function of isotropic damping. And when you get the rate equivalent signal of this force, as you will see, it is very similar to your main signal, this anisotropic error. So if you know the correlation between this anisotropic error and isotropic error, in the background, you can easily compensate this error. So the question is, what is this alpha coefficient? What is this correlation? You can easily calibrate this with single point calibration before you run your operation or during the fabrication procedure, because it is just set by the ratio between this zero rate output and this omega drive. So this method will suppress the anisotropic damping. So now let's talk about the test results. We got the sensor module of a commercial product. You can get this sensor from the market. So it's a good sensor by itself. It's a perfectly symmetric structure. It has a linear transduction because it's a magnetic sensor. It's mode matched. So first we made the scale factor test between 15 Celsius to 45 Celsius. And as you can see, the scale factor varied a lot. So the peak-to-peak deviation is around 20,000 ppm. It's huge. But once we made our scale factor calibration technique, it is just 61 ppm. So the amount of the improvement is in fact more than 300x. So I think we can see that the scale factor method that we propose is really effective. So what about the bias? First, we got the deviation for uncalibrated output. So when we apply this phase error calibration, as you can see, the bias stability is improved by a factor of 2. And now, and this phase error correction is basically avoids this quadrature leakage. But now, after this quadrature problem, we have still this anisotropic error. And once we apply this anisotropic error compensation, the overall improvement is now around 7 for tau is equal to 400 seconds. And in addition to that, we also made the TCF, the temperature test for bias. And after we apply all calibration techniques, the TCF of the bias is reduced by a factor of 4. So to conclude, in order to improve the MEMS gyroscope, we don't need to increase the cost or power by applying background calibration technique. It is possible to improve the performance of the gyroscope considerably. And as we see here, the scale factor is improved more than by a factor of 300. The bias stability is improved by a factor of 7, and the TCF of the bias is reduced by a factor of 4. Thank you for listening. I would like to answer your questions.
Thank you.